this week. Fiber bundles and symmetry groups by Aaron.
All right, cool. Thank you. All right, so thank you guys for having me. A quick warning ahead of time. After rereading my notes, this is an incredibly ambitious talk. We're going to get through what we can, but you know, fiber bundles and symmetry groups may be a little bit more than what we'll actually talk about. So here's the talk: fiber bundles and symmetry groups. Okay. So before we can really get into the main topic of conversation here, which is fiber bundles, we need to get comfortable with this idea of non-canonical isomorphism. So I just want to do a couple of examples and then, you know, sketch a little proof of a theorem for you that tells you kind of the sort of things we're going to be working with. So section 1, non-canonical isomorphism. Okay, and if you guys have any questions or anything, feel free to interrupt me and we'll try and get it sorted out. Okay, so the idea of non-canonical isomorphism is something that shows up whenever you're dealing with an object that has symmetries associated to it. So let's just work with an example. So here's a square, and just so that we can keep track of things a little bit, I'm going to label it like that. And now here's another square labeled in a totally different way. Okay. So both of these are squares, right? So they're essentially the same sort of object, right? A square is a square. It just has 4 sides. They're all the same length. So what we would say is these squares are isomorphic. Okay. But in order to be really precise about this notion, you have to actually give an isomorphism between these things. You need to figure out a way to identify this square with this square. Okay. So what's one way we could do that? Any takers? It's maybe the most obvious way that we could identify this one with this one. Huh? Yeah, just sort of lay it on top of itself like that. So A goes to purple, B goes to very light green, D goes to yellow, and C goes to pink. Okay? That's a way of matching up this square with this square. This is an isomorphism, right? Are there any others? Okay, what's another way I could do it?
You could just change A and C.
Huh? Change A and C? Okay. So you're saying somehow do what? Yeah. So A goes down to pink. Sorry for the color overloading here. This still goes here. This goes up here. And that goes there. So that's another totally valid way of identifying these two squares. Clearly there's some more, right? Here's the question. Is any of them better than the rest of them? For anything. I mean, can you think of any particular reason why A should go to pink always? What if instead of pink, this was labeled B? Right? The idea is somehow these things are the same object. They're both squares. But the way that we identify one with the other is important information. So we say the two squares are non-canonically isomorphic. Okay, this non-canonically business essentially means I have two examples of the same sort of thing, and if I ask one person to match them up, they'll give me one answer. If I ask another person, I might get a completely different answer. And there's no preferred way. Okay, What about other examples of things that exhibit this sort of phenomenon? Yeah?
Does it matter that in the case where you flip the A and C, the orientation reverses?
Depending on what you count as a symmetry of the square, it could, but we could just as easily talk about identifying by a rotation, in which case that problem would go away. But yes, that's a good question. Somehow, the structure that we want to preserve is part of this data. I mean, if every one of these had a direction associated to it, maybe we want to preserve that direction. That gives us fewer ways to identify one with the other. That's a good point. Okay. So what about another example that maybe you saw in your first or second year here of another situation where this happens? Perhaps from your linear algebra class. So let's say V is an n-dimensional vector space. Okay. What do we know about n-dimensional vector spaces? They're all isomorphic, and they're all isomorphic to Rn. So this is isomorphic to Rn, essentially by picking a basis. Right? Every vector space has a basis, and each basis gives me a way to identify it with Rn. Okay? But we know that vector spaces have lots and lots of bases, right? Generically, tons of them. Okay? So here's the question. How many bases does V have? Okay, so certainly a number is not going to suffice here, right? Because it's infinitely many. But is there a way that we can identify what sort of structure the set of all bases has? Let's try doing the following thing. So let's say here's my V, and a basis is an isomorphism F with Rn that I'll just draw this way. Okay? It sends my first basis vector down here to my first basis vector here. So this is a basis. And so on and so forth. Okay? Let's say I have another basis like that. Okay. How are these guys related? You can rotate Rn, or you can sort of change the sizes of things. You can skew angles a little bit. Essentially, all of the different bases that you can give V differ by a change of basis down here. Okay? So here's the first little theorem that is the linear algebra version of what we're going to be dealing with. And let me make sure I write this down properly. Okay. There is a non-unique isomorphism of sets. Okay, just the set bijection. There's a little bit more structure here, but we're not going to worry about that currently. Here is the set of bases for V. And what's going to go on this other side here is all of the ways that I can change my basis down here, automorphisms of my fixed sort of example. So this is invertible n by n matrices. Okay. So let's do a little bit of a sketch proof here, just to see exactly what's going on. So a basis for V is a map like this, right? Okay. So let's fix a basis F. So this is an isomorphism from Rn to V. Okay? So now, given another basis G, how am I going to produce an invertible n by n matrix, an automorphism of Rn? Any ideas? Yeah, something like that. What I'm going to do is essentially just use the fact that this arrow goes the other way too. I can actually get something which is G inverse composed with F. This is an isomorphism of Rn to itself. Everyone follow? Okay. So this is an n by n matrix. Cool? So that's one direction. Now given what I'll call H, so given an invertible matrix, how am I going to get another basis from F? So here, I got an automorphism of Rn by doing that. Here I have an H. I have this F. I want some new G. I guess really what I want is it going this way. So what I can do is get G by first changing Rn and then applying my basis. So this gives me a basis, which I need to make sure I get this right. H compose F. V. Okay, so what happened here was I picked a basis to begin with, and once I did that, I could get between all of my bases for V and all of my invertible matrices. Okay? So the point that I want to make here is this is not a linear algebra statement. This is a statement about any sort of object with automorphisms. In particular, it applies to our square example here. So let's think about our two ways of identifying these two squares together. How do they differ? So they both send D to yellow, they both send B to green, but they're sort of flipped over here. So their difference sort of corresponds to the automorphism of this square, which flips. Okay? All right. So the thing that I want to point out here is we have sort of the following principle. So meta theorem there is a non-unique isomorphism of sets. So I'm going to write isomorphisms x to x prime, assuming there exists at least one, with isomorphisms of x with itself. And this I'm going to call x. Okay, but the fact that this is only of sets is important because this thing is a group, right? This is the symmetry group for whatever my x is. X can be a square, it can be a vector space, it can be, all sorts of different things. This is not a group. This is most assuredly not a group, right? There's no way I can compose any of these things together. But still, if I sort of pick one of these things, it's completely identified with that group. Okay, so that's kind of a long digression before we really get to the good stuff, but are there any questions about this concept? Okay, so now what maybe you all came to hear about, fiber bundles. Okay. So here's the idea of fiber bundles. Okay, so the idea is essentially the following. So let's say that I have B, which is some nice topological space. If you know what a manifold is, that's perfect. You can get a little bit more general than that, but manifold is certainly something to keep in mind. It's just something that isn't too badly behaved. Okay, so now roughly, a fiber bundle over B with fiber F is an assignment to each point in B an object. So it could be just a topological space or something with more structure. An object isomorphic to F such that I guess I'll say they vary continuously. Okay, so essentially the idea is I have this apparatus which has a little base space which I can think of as like a space of parameters. And for every parameter I have some object that is of a particular isomorphism type but is not, you know, just the particular example of that thing. And that's essentially the reason that we get sort of twisted objects. So let me give you a few examples so you can see the twisting, and then we'll talk about some cool stuff. Okay, so examples. So let's just say that our fiber F here is, say, the interval 0, 1. Okay, it's just a topological interval, and I'm going to say this thing only has essentially two automorphisms. Either it stays the same or I can flip it. Okay, so what are, so I guess I'll write that. So what are F bundles over, say, S1? So the circle is what we're going to mostly be concerned with today, hopefully the two-sphere if we get to it. But let's talk a little bit about what sort of objects we're getting here. All right. So who can think of one example of something where I have an interval assigned to every single point on the circle? Okay, that's the harder one, but that totally works. So Mobius band over here. We also just have a cylinder. Okay, so a cylinder is just something like this. I've got a circle. I've got a couple of other circles like this. And my fibers are these intervals here in pink. So sorry, this picture is a little bit tough to see. Maybe that helped. But essentially what we've got is sort of just around this circle, I have a bunch of intervals. Okay? The other example, as we said, is a Mobius band. So this looks something like this. And it's going to be our primary example later on. Okay, so something like this. All right, so in these pictures, I have the fiber labeled by the pink, so that's F, it's my interval. I have my base space, the circle, labeled by B. Okay. So these are definitely two examples of bundles with fiber 0, 1 over the circle. And I hope by the end of this talk to convince you that these are the only ones. Okay. Let's see, what other example did I have? Yeah, okay. So here's an example that's a little bit more complicated, but extremely relevant. Okay. So think about S2 sitting inside of R3, just the unit sphere. Okay. This guy looks something like this. Okay. And I have some coordinate axes like that, like that, like that. Cool. All right. So this has a very, very natural bundle associated to it, where the fiber is a two-dimensional vector space. So here's the way that that's constructed. Let's pick a point here. That point is the same thing as a vector. Actually, I'll do this in pink. As a vector of unit length from the origin. Cool? Okay. There's a two-dimensional vector space associated to this vector, which is just the perpendicular plane. So this is the perpendicular plane to V. Okay, that's a two-dimensional subspace of R3. Okay, and as I move my points around on my sphere, I get a two-dimensional vector space for each one of them. Okay, so this is called the tangent bundle. To S2. And this has this really sort of neat property. It turns out that it's not what we would say trivial. This is not equivalent to S2 cross R2. So over here, we had these two examples. This one was just a product, right? This thing is just, I pick a point down here in my circle, and I pick a point in my fiber, and that completely determines everything. In fact, it determines an isomorphism with the space S1 cross 0, 1. Okay? Here I can't do that. Because if I could, I wouldn't have this flip, essentially. This is not isomorphic to S1 cross 0, 1. And the fact that this is not isomorphic to S2 cross R2 is what's called the Hairy-Ball theorem. Because what ends up happening here is if it were, you'd be able to essentially comb all of the hairs on the surface of this sphere. You can't do that. Okay, so that was pretty rapid fire. Are there any questions so far? Okay, so it's 5:25. We're in good shape. All right. So now let me give you a precise definition of fiber bundle, and we'll see if we can make some sense of it briefly. And then we'll get to the Mobius band. Okay. So this sort of assignment of a particular object to every point takes a lot of work to really make precise. It's actually easier to go another route. So what we usually do is we give the following definition. So a fiber bundle is a continuous map P from some topological space E to another topological space B. Suppose if you want to, you can assume that they're both manifolds, or you could not, and that's fine too. With the following property, such that for every point in the base, point B in the base, there exists an open neighborhood B in U subset B open and an isomorphism. So call it F. So this goes from the preimage of P, or the preimage of U under P, to U cross F, and it needs to satisfy some properties. So the first property is that somehow we want these F's to sort of match up with the fibers. So how did I write that? So P, I guess when restricted to U, has to be equal to F followed by the projection onto the first factor. So explicitly what this means is, this P is telling me essentially what point in my base any point lies above. Okay? This is telling me that I don't change what point in U anything lies above. So when I write down such an isomorphism here, it'll take this pink line to the right place. Everybody okay with that bit of it? All right. The second one, and this seems a little bit strange, but it turns out that it's actually important in places. The restriction of F to any B prime in U, I guess P inverse B prime in U, is an isomorphism with F. Okay, so this is a little bit technical. It's mostly saying something to the effect of, if I have a situation like this where my fiber is a vector space, then this map, F, is actually a linear map between all of the vector spaces. In fact, it's a linear isomorphism. It preserves whatever sort of structure I had. So it's a little bit technical, but it's saying essentially this thing is in this little neighborhood U exactly like just this trivial thing. Okay. All good with that? So unfortunately, that's a little bit technical. And really, we won't need it so much. But it's good to have it. Okay. And I guess I've already said this, but we call a bundle trivial if it's just a product. Okay. So, all right. I guess with the remaining time, I'm going to tell you how to classify all fiber bundles with all fibers over the circle. And that's going to give us exactly sort of the non-canonical isomorphism stuff we were dealing with before. Okay. So let's see. Yeah, okay. So I guess I'll just tell you the theorem. So theorem. So suppose our fiber F has a discrete automorphism group. G. Okay, so this holds in all of the situations that we've dealt with except for the vector spaces. Certainly with the square, our automorphism group, I couldn't continuously change from one automorphism to another. So it's just a bit of a, it's a little bit important here, but there's ways around it. So if this happens, then there is a natural isomorphism, or I guess I'll say correspondence, between F bundles on the circle and I guess we're already calling it G and G. Okay, so here's this weird thing where I spent all of this time talking about non-canonical isomorphism and automorphism groups. And here I'm telling you that two things are naturally identified. And weirdly enough, the reason that you have this natural identification is because you didn't before. So that'll come out in the proof here. So does everybody understand the statement? Okay. All right, so now we'll get to the props and then probably call it. So first thing I need to do is convince you that over an interval, every bundle is trivial. Okay. So here's our strategy. We're going to think of the circle S1 as the interval D1. I like to use -1 to 1 with 1 and -1 glued together. Okay, so here's a picture of D1. If I glue the two yellow things together, what do I get? I get a circle. Okay. So ultimately our strategy is going to be building bundles over S1 by gluing fibers together, and then starting with bundles, cutting them, and identifying the automorphism. Okay. So here's the technical thing that makes that happen. Technical lemma. Every F bundle over or with base D1 is trivial. All right. So why should this be? So what I have to begin with is, where's my pink chalk? Ah, cool, thanks. All right, so what I start with is some bundle with fiber F over the interval. And let's say it's trivial here. Then in that little neighborhood, it looks just like a product. Cool? So here it's trivial. Okay. If I pick a point immediately outside of here, this also has a neighborhood where it's trivial. And roughly I can glue those trivializations together. So trivial longer, I guess. And the idea is you just push it all the way out. Okay. If you want to visualize this, it's something like you start with something that's all twisty, and then in a little patch you can untwist it. You get out to here, you can untwist it a little bit more. You get out here, you can untwist it a little bit more. And that's roughly what's going on. Without getting a little bit more precise, that's what's happening. And this is going to make everything work. Cool? All right. So now, let's finish this off. Okay, so back to the theorem. So let's say I have an automorphism of this thing. Then I can form a bundle over S1 by gluing along that aught. And here's where the props come in. All right. So here I'm going to be talking about bundles with fiber the interval over the circle. So the interval, I said, has basically two automorphisms. It has the trivial one and the twist. Okay? So what happens if I just glue along the trivial guy here? Got myself a cylinder. Cool? What happens now if instead of doing that, I twist and then glue? This part's always tricky. There we go. So I twisted, I'm gluing. And wouldn't you know it, I've got myself a Mobius band. Okay? Good? Everybody cool with that construction? All right. And you know, that was I essentially only had two of them, but you could imagine the situation of the square earlier. I could take, say, like a square-shaped slinky, rotate it by 90 degrees, and stick it onto itself. And that'll give me something that's like a square over the circle. Good to go? Yeah, I thought so. Just wait. I think this next part's even cooler. All right. So we've done one direction. So this was starting with an automorphism. We got a bundle. OK. So now, let's say I'm given a bundle. What I want to do is I want to mark, or sorry, I want to cut the bundle to get 1 over D1. OK? So just undo the gluing, or even just cut it. And what I have now is a bundle over the interval. OK? This is trivial. So I'm going to call it E prime. So pick an isomorphism E prime with D1 cross F. OK? Good so far? All right. Now here's where the non-canonical isomorphism stuff comes in. And this is what I think is really cool. So the isomorphisms F restricted to, I'm just going to say F restricted to -1 and F restricted to 1 are both identifications of this object that's isomorphic to F with F itself. Are bases. So I can use one of them to make the other one correspond to an automorphism. Use one to make the other correspond to something in my automorphism group. Okay, so that's a little bit cryptic, but luckily we can see it with these guys too. So here's what I'm going to do. I'm just going to give myself something to latch onto. I'm just going to mark something there. And I'm going to mark something here. Okay? Now look what happens if I just cut this guy. I now have a trivial bundle over the interval where I can identify that it was not glued by any non-trivial automorphism, because these guys are in the same spots. On the other hand, say I cut this guy. Then voila, they're in different spots. I can completely recover the automorphism I used to build it just by cutting this thing open. Okay? So that's how that goes. And it just sort of works for everything. Okay? And really the sort of important thing was that we had these two different ways of identifying with F. And then we could use this stuff we did at the beginning to make that actually correspond rigidly and naturally to an automorphism. So that's that natural thing in the theorem that I erased. Okay, so still got a little bit of time here. Are there any questions about this before I move on to slightly more advanced topics? Yeah?
How does this show that you can't have a different fiber bundle of interval over S? So how come you can't twist it more than once?
Yeah, it really sort of doesn't. I'm fudging things a little bit. You have to actually show that that would give you nothing new. But you can kind of give an explicit map that'll do that. So you're right. There's something I'm leaving out here, but twisting it more than once, it doesn't change anything. Yeah. You could imagine kind of, it's twisted twice in 3 dimensions, but there's a way to sort of untwist it if you have a little bit more room to work in. That's one way you can think about it. I mean, that's something to the effect of the statement that there's no such thing as a knot in R4. Yeah, something like that. Okay, other questions about this? Okay, so let me leave you with a couple of things to think about. First off, we've really only been talking about bundles over S1, but we can actually, do this very, very generally. Let me give you a couple indications about how that happens. So actually, I guess the natural first thing to do is now suppose that G is not discrete. Okay, so what's an example of some object that has a non-discrete automorphism group? Maybe the simplest one you can think of. Circle. I like circles better. Lines are going to reduce to what we just did. But a circle. Okay. So the circle itself, S1, doing a little bit of fudging here. Let's say I really only want to consider things that are fairly rigid. I don't want to squash or squeeze or anything. It tells me that my automorphisms of S1 are essentially S1 themselves. I guess if you allow the flip, then it's something like that. But let's say we keep the orientation the same. Then the only thing you can do is rotate this guy, right? Okay, so what this tells us is essentially we can move between different automorphisms. And the question is, how is that going to affect our classification here? So, any ideas about what sort of behavior we might see here? Well, let's do the following thing. So, let's say I pick some f in my automorphism group, and I use it to identify the circle here with the circle here. That gives me a circle bundle over the circle. Reasonable? Okay. What about if I pick some f prime? Well, because the circle is connected, I can sort of move between f and f prime and actually get another bundle. And what this picture is hopefully trying to communicate is I have enough room to sort of wiggle between the f and the f prime. And without getting into too much detail, f and f prime give equivalent bundles. Okay. So this is an example of a very general principle at play here, which is that everything here is invariant under small perturbations or homotopies. And what this essentially gives us, if we go through and run the same argument, is the following statement. So I'm just going to write f bundles over S1 are naturally identified with connected components of G. Somehow, if I can move between automorphisms along a path, I get the same bundle. So this is the first indication that we have a little bit of wiggle room here. Somehow, equivalence classes are very discrete objects, whereas maps to the symmetry group are hugely non-discrete objects. Okay, so this is the sort of first thing that happens, but it actually gives us a hint about the next thing that's going to happen. What time is it, incidentally? 50. 50? Okay, so one last theorem and then I'm done? Okay. Usually, always, most of the time late?
Occasionally.
Perhaps. All right. Okay, so how about bundles over the two-sphere? Okay. Remember our example of the tangent bundle to the two-sphere. That was, definitely something that's going to have a non-discrete automorphism group of the fibers. In fact, works out to be essentially S1. But, it's not obvious that our techniques here are really going to work. The fact that they do is awesome. So, is there a question? Okay. So let me just give you this to think about. Think about S2 as D2. So this is vectors in R2 with norm less than or equal to 1 with S1, just the unit circle, collapsed to a point. Okay, so this is maybe a little bit trickier to visualize, but let me try and draw a picture for you. So I'm saying start with the solid two-dimensional disk, then, so it's all solid in here, identify all boundary points, and what I have is the disk that I had before, now with that entire circle, that single point up at the North Pole. Okay? So I'm just taking this thing, scrunching it all up together. All right? So now, let's try and build some bundles. Over S2. Well, just like before, this two-dimensional disk is a simple enough space where all bundles over it are trivial. So all F bundles over the two disk are trivial. Okay? So now all we have to do is worry about all the ways that we could potentially glue all of these fibers together to form the fiber at the North Pole. Okay? What's that going to be like? So if I want to build a bundle by choosing an isomorphism of, let's say, E restricted to X, isomorphic with F, for each X in the boundary S1. So I'm picking kind of like a basis for every vector space along this boundary circle, if you want to think about a vector space. Or more generally, I'm picking kind of a way to identify the interval or a way to twist the circle, something like that. This is the same thing virtually by what we did earlier, sort of a topological version of it, as a map from the circle into my automorphism group. Okay? So given a map from the circle into my automorphism group, I get a bundle. And it turns out by puncturing and using this thing, I can recover a map from any bundle. But I still have this wiggling business. And let me just write up the last theorem, and then we'll be done. So F bundles over S2 are naturally identified with the fundamental group of G. So if you've taken topology, maybe you know what this is. But essentially what it means is maps of a circle in modulo homotopy, modulo moving them around. Okay? So this is, you know, maps S1 to G, modulo continuous deformation. So this is kind of neat, because it gives us a way, just by knowing what G looks like, to know everything about bundles over S2. And you know, thinking about how to make all of that work out is awesome. Also, everything we did here generalizes to higher dimensional spheres. And in fact, it works for every single space ever if you do it right. So that's what I want to leave you with. Thanks. Am I done?
Done.
I'm done.